Okay, so continuing on in alkenes and alkynes, for predicting the products of the addition reactions, there are three things we need to ask ourselves. We need to ask, what are the identities of the groups adding across the pi bond? What is the expected regiochemistry? Where does the more electronegative atom add? Where does the less electronegative atom add? And what is the expected stereospecificity of the addition, syn or anti-addition, or you don't have to worry about it. To answer these questions correctly, it requires a lot of study time and working problems out of both the back of the chapter and out of the PDF, and just thinking about what's going on as you're doing them. By the time the test rolls around, you'll need to be able to look at a certain reagent and think about what it can do to an alkene or an alkyne, and write down pretty quickly what the product of the reaction would be. If you need to draw you a short mechanism, you can in the predict the products. I don't grade that part, but if you need to do that to help you out, feel free. So, synthetic strategies. In this chapter, we're far enough into organic that we can do things, small multi-step syntheses, to change one thing to another, one substrate to another. And here we have an example of a 2-bromo-3-methyl butane that we want to turn into 2-bromo-2-methyl butane. Now, when we look at this, we know the only way we can form, well, there are two ways we can form an alkyl bromide. We can take an alkane and we can brominate it with bromine and light, and that would add a bromine onto the more substituted carbon. So if we could turn our starting alkyl halide into an alkane, we could brominate it and be there. But we're not in the alkanes. We've learned about alkenes and alkynes. We're starting with alkenes. We'll work on alkynes, but they all do the same thing. So somewhere in this problem, there's going to have to be an alkene or an alkyne, because that's what chapter we're in. So the best way to make the more substituted alkyl bromide is where we take an alkene and we add HBr to it. The hydrogen goes to the less substituted carbon, the bromine goes to the more substituted carbon. So then we're down to, how can we force the elimination to form the alkene in the more substituted double bond, the more stable one. And the best way to do this would be a small base that would form the alkene there. Okay, so in this problem, it is a two-step problem where we need to eliminate to the alkene and then add HBr. And in any of these multi-step problems that you will see in the homework and on the test, they're probably going to go through an alkene at some point in there, or an alkyne, as we get closer to the test, in what has to happen. So how can we eliminate things? We have the Zaitsev elimination, where we have to form the more stable alkene. And we have the Hoffman elimination, where we form, so this is the thermodynamic product, more stable, or this is the kinetic product, the easier to form. So we have the possibility from any alkyl halide of forming the more substituted alkene or the less substituted alkene, if there is a difference in, if it's not symmetrical around the alkyl halide. So we have to think about this type of thing as we're going forward. If we want the more substituted alkene, we have to go with a very small methoxide, ethoxide, a small base that can do the E2 to make the more stable one. If we want the less substituted one, we need the big bulky T-butoxide to do an E2 to make the alkene we want. And just remember, E2 is best in the eliminations, because in the E1 you form a cation. If you form a cation, it will rearrange if it can. Okay, so we have to be careful about that, what type of reaction we're going to do in all of these. Okay, so we control what we want to do to. So here's a review of alkenes. In this first one, we want to draw the product for the following reactions and draw the mechanism for the first step. We don't have to draw the mechanism for everything, just the first step. The second step in both of these we will not cover in this class. Okay, the second step of the oxymercuration is a free radical thing. We won't go there. The second one is a nice rearrangement. It's a cool step, but we won't talk about it in this class. We'll worry about it later. Okay, so in all of these reactions, the pi bond attacks the least electronegative atom, which in this case is the mercury. It's got two acetates. We'll draw one out. Okay, the mercury can form a partial bond back to the more substituted side of the alkene, so we get a partial three-membered ring with a partial positive on both the carbon and the mercury. Then our water can add to the more substituted carbon, breaking open the three-membered ring, giving us the mercury out on the less substituted carbon. That gives us this. And then the acetate, our best base in solution, comes and grabs the extra hydrogen off of this. So after step one, we have drawn this before, and I'm realizing I don't have near enough space for it. So after step one, we have the mercury on the less substituted carbon and the oxygen on the more substituted carbon, and then in the second step we add the sodium borohydride. And the only thing that doesn't belong in an organic molecule for Org 1 or Org 2 class is the mercury. So we reduce it off, add a hydrogen out there to go with the other two hydrogens, and put the oxygen on the more substituted carbon. So we've added water across the pi bond, with the oxygen of the water adding to the more substituted side. Now in the second one, I'm going to have to add a page where we have, now this last step down here, draw the mechanism for the following reaction. We have acidic water. We need to draw it out so we have the hydrogen we need. The pi bond goes and attacks the hydrogen, the less electronegative atom. It goes to the less substituted carbon, so it's out here. We have two of them there now. And then our water, the more electronegative atom, adds to the more substituted carbon. And, well, remember, you don't have to draw those hydrogens in. We can draw them in just for fun. Then we have to remove the extra hydrogen off of our acidic alcohol, and we get the product of the reaction. So we've added, in all three of these examples, we've added water across the pi bond. In the first example with the mercury acetate, we added the oxygen to the more substituted carbon. In the second one, the borane, on the acidic water, we added the oxygen to the more substituted carbon. So mercury acetate or acidic water are similar in how they add things. Okay, so they are two things that will do much the same thing if there are no side reactions that can occur. Our alkene, we react it with BH3 in the first step. The pi bond attacks the least electronegative atom, which in this case is the boron. As it attacks the boron, we transfer the hydrogen over to the more substituted side. They add at the same time, so they're going to be on the same side. If we have to worry about, in this one we don't have to worry about it because we have multiple hydrogens on each end. We don't form anything special. special. But if it were in a ring or something, we'd have to be careful to show that they add to the same side. And then we add hydrogen peroxide and hydroxide, and we oxidize off the borane, and we're left with, replacing it with what we have in solution, is the oxygen. So the oxygen adds to the less substituted carbon of the double bond, the hydrogen to the more substituted, because in the initial step, the boron was the less electronegative atom, and the hydrogen was the more electronegative atom, and the less electronegative atom always goes to the less substituted carbon, no matter what. And then in the work in the second step, where we add the hydroxide and hydrogen peroxide, what can we replace the boron with? All we have is a bunch of oxygen, so we end up putting an oxygen on in place of the borane. We added the oxygen to the less substituted carbon, and in the third. Okay, so side reactions. If we have this alkene here and we add acidic water to it, we know the first thing that happens is the pi bond attacks the proton, forming the more stable cation. Then what can happen to this? We have water to a secondary cation, or we have a tertiary hydrogen that could rearrange. So we have it migrate over to form a new cation, and then the water can add to that. And then we can take off the most stable, or the extra hydrogen, to form our alcohol, and we get this. So what happened in this reaction? We formed a secondary cation in the first step, and it rearranged. So with just acidic water, we have to be very careful, because a rearrangement can occur. Okay, the mercury acetate in water followed by sodium borohydride will not rearrange, but just acidic water or acidic alcohol adding in, it will rearrange if we don't form the more stable cation initially. In this one down at the bottom, we attack the hydrogen because it's a less electronegative. It goes to the less substituted, form the more stable cation, and then the bromide adds to that, and we form our alkyl bromide. Okay, and one thing you'll notice in all of these reactions, the pi bond attacks the least electronegative atom. It goes to the least substituted carbon, and then the more electronegative atom goes to the more substituted carbon. Pi bond attacks a hydrogen. It goes to the less substituted carbon, the more stable cation. It's a secondary cation, so it has to rearrange to a different, more stable cation, tertiary one. It's 3 methyls. We don't have to worry about what rearranges. Just one of those 3 methyls rearranges, and we get the bromide adding to that tertiary cation. The one below, we have Br2, and the pi bond attacks one of the bromines. We kick out the bromine off of it as a leaving group, and then the bromine can add to the more substituted side of the double bond. So all 3 of those arrows happen at once. So in this one, we are forming a bromonium ion. We have to be careful where we put it. So we have the bromonium ion coming out towards us, and then whenever we have a positive charge in the 3-membered ring, the nucleophile always adds to the less substituted or the more substituted carbon, breaking the 3-membered ring, giving us our product. Okay, and it always adds to in the 3-membered ring. If you have a positive charge, it doesn't matter what atom it is. If there is a positive charge in 3-membered ring, nucleophile always adds to more substituted carbon always. Okay, so be careful about that so you always get the right product. If there's a positive charge in the 3-membered ring, and we'll draw a couple more as we're going along in this, but if there is a positive charge in that, we will always add the nucleophile to the more substituted carbon. So here we have bromine and water, so we're going to do the same sort of thing, have the pi bond attack the bromine, kick out a bromine, and have the Br come back and form the bromonium ion. Now we get in these, we get both bromine coming back and bromine coming forward. We only have to draw one of them, because if you can draw one of them, you can draw the other one. Okay, so we have the bromonium ion. The water has to add to the more substituted side. So that gets us to bromine going back, methyl, or bromine coming forward, methyl coming forward, water going back, positive charge on it, and then we have to take the extra hydrogen off of it to form the halohydrin. Okay, so here are some reactions like what would be on the test. You should be able to go through and quickly write down what's going to happen. The ones with a little star on them. Mechanism for what it says. Most of them, it's the whole thing. D and E is only the first step. Okay, so you should be able to draw any of those mechanisms as you're going along. In the first one here, we add the hydrogen onto the end, forming the secondary cation. It rearranges, and then water adds the more substituted carbon. Okay, try drawing the mechanisms for these as we're going through. If you have a question, send me an email, and we can talk about it via email. Send a PDF, make it a small size PDF, and you can email it to me at dnew@uco.edu. The next one, we add the bromine to the more substituted carbon. The next one is a free radical, where we add the bromine to the less substituted carbon. Okay. The next one, D, is the mercury acetate and water. We put the oxygen on the more substituted side. Then the hydroboration puts it on the less substituted side. So here we end up making the transdiol with the oxygen that added, that we need to keep track of, is there. So, and I'm going to go to the next page, add a page in here, draw the mechanism for this, and then we'll add another one and draw the mechanism for the next one. So in this, we have an epoxide going back, and then we're adding. Okay, so that's how we got that one. In the next one, we end up doing an SN2 type reaction. So we all know in an SN2, the oxygen, or the nucleophile, comes in from the backside. So in the next one, we have that same epoxide, and we add oxygen 18 labeled hydroxide, and figuring out what can happen. Okay, in the next one, hydrogen, all we have is hydrogen gas to add. So we're going to add a hydrogen onto each side of the double bond. They're going to add at the same time, so we end up with the hydrogens adding into one another. Okay, so we have to show that in our product. The next one, the peracid, you should be able to draw the mechanism for the forming of the epoxide. So, and remember, in these, we get both possible stereochemical outcomes going forward and coming back, but you only have to draw one of them. So we drew the epoxide going back with acidic water. We're going to end up with the oxygen we add in the acidic water, adding to the more substituted side, so it's going to come from the back side of the epoxide that was going back, or the front side, which we'll draw a mechanism for over here. And in an SN2 mechanism, remember, the nucleophile adds from the back side. It attacks to the least substituted carbon it can go for. So it's going to go for the secondary one over the tertiary one. Add the oxygen 18. Open up the 3-membered ring, give us an O-, and our oxygen 18 hydroxide is there. The O- is going to go grab a hydrogen off of water. That's an oxygen 18 labeled water, but it doesn't matter. So you're just grabbing the hydrogen. And that gives us our product with the regular oxygen, the oxygen 16 going back, and the oxygen 18 label coming towards us. And this is the other example of the anti-dihydroxylation. Okay, so you can do that with either acid or base to an epoxide, and if we add oxygen 18 labeled water and hydroxide or acid in there, we can track where the 18 ends up, so it helps us with the mechanism. So we have that oxygen 18 label. So the first thing that happens is we protonate our epoxide. And we have this. Now this, we're going to add, we have our oxygen 18 labeled water. It's going to add to the more substituted carbon, breaking open the epoxide. So it's going to send our methyl back. Our OH that was on there is back, and our oxygen 18 labeled water adds from the front side. We need to keep that oxygen 18 on there each step along the way, and we have a positive charge, and then we add water to it to pull off an extra hydrogen, and that gives us where the oxygen 18 is coming towards us. Whoops. The methyl is going back, and the other oxygen is going back. So it gives us the anti-diol where the oxygen 18 compound atom added to the more substituted side of the epoxide. These 3 pages, you should be able to draw the water with an oxygen 18 label. So there's those 2 mechanisms. Then we have J here, which is just an SN2, where the hydroxide is a good nucleophile, the tosylate is a good leaving group. We invert the stereochemistry. And we get this. Now you should be able to prove to yourself that the starting material in J is S, and the product of J is R, so that we can show that it does invert stereochemistry, because we know in an SN2, if we have a stereocenter, it is inverted. Okay, K, CH2I2, zinc, and copper reacts as if we had a carbene, where we have a CH2 with a lone pair on it. Okay. So we get that. Then the next one, Br2, we know it adds the bromines anti to one another. Okay. If we aren't drawing a mechanism, we can just draw them anti. It doesn't matter how we do that. If we're drawing a mechanism, then we have to be careful that from the bromonium ion, the three-membered ring, which side do we open it up at and where does it go? Okay. The last one down here is very similar to it in that it adds an oxygen to the more substituted and bromine to the less. Then M, ozonolysis, is M and O. Ozonolysis completely cleaves the pi bond, cuts sigma and pi, everything. So we broke two bonds between the two carbons, so we're going to have to replace those with bonds to oxygen. Now, if we have hydrogen peroxide or the potassium permanganate and have a hydrogen on the alkene, that carbon gets oxidized up to the carboxylic acid, so this one would give us ketones and acids. The one at the bottom, zinc and water, is a reducing agent, so after we cleave the carbon-carbon double bond, we're going to get ketones and aldehydes. Okay, so zinc and water or dimethyl sulfide gives aldehydes, hydrogen peroxide and ozonolysis gives us carboxylic acids. Osmium tetroxide or cold dilute potassium permanganate doesn't break all of the bonds, it only breaks pi bonds, so it's going to give us a bond to oxygen on each of them. If we have a single bond, if we're breaking one carbon-carbon bond and replacing it with one bond to oxygen on each carbon, we have to have a hydrogen on there, so we're going to get the syndiol in both of those, the osmium tetroxide or the cold dilute potassium bicarbonate, potassium permanganate, excuse me. Now, if we think about this, where we formed a carbene like structure. Now this isn't a full-fledged carbene, it reacts as a carbenoid like a carbene, but to talk about what can happen in it, we'll do it just as a straight carbene. But that carbon right there has a formal charge of 0 because it has 2 bonds and 1 lone pair, 4 electrons around it. Carbon on the periodic table has 4 valence electrons, so 4 minus 4 gives us a formal charge of 0. It is electron rich and electron poor in that it has 3 orbitals used, 1 is empty, so the pi bond can add to the empty orbital, and then the lone pair can add to the other side of the pi bond, and we end up with a 3-membered ring where we have added a CH2 across our carbon-carbon double bond. Okay, so 2 pages. Here we have some problems. And in these are really neat problems. They're problems out of an old textbook. We need to look at what can happen. So we have, from the ozonolysis, we get this tricarbonyl compound and formaldehyde. So from the ozonolysis, we get, followed by zinc and water, we get 4 carbonyls out of it. If we take our starting material and react it with hydrogen and platinum, it tells us we get the 1 isopropyl 4-methyl cyclohexane. So from this is enough information that we can figure out what the structure of limonene is, because from the ozonolysis we're given the information of where the pi bonds are, because in the ozonolysis all we do is react a pi bond, whether it's a double bond or a triple bond, with the ozone. We completely cleave it to form carbonyls. If we take an alkene and add hydrogen to it, all we end up doing is getting rid of the double bond. So the carbon skeleton for limonene is going to have this basic carbon skeleton that we got from the reduction. And what we have to do is figure out where do the double bonds go in that. And from seeing that we have 4 carbonyls formed from the ozonolysis, that tells us that each ozonolysis forms 2 carbonyls, so there has to be 2 pi bonds in limonene. Okay, so then we have to figure out where are they. Now, we get just a formaldehyde, a 1 carbon piece with 2 hydrogens on it, so there has to be a double bond going out to a methyl somewhere in the structure of limonene. And there can only be 1 double bond within the ring of limonene because we get this tricarbonyl compound. Okay, if there were 2 double bonds in there in the structure of limonene, we'd get bigger pieces or smaller pieces of a molecule, but more of them. So we need to count from a carbonyl. If we go from those 2, it's only 4 carbon ring if they came from the ring. So those 2 can't be part of the ring system. If we go here, those 2 are 6 carbons, counting the carbonyl, are 6 carbons apart. And if we went from the ketone here, 2, 3, 4, 5, so the only 2 carbonyls that can come from an alkene in the ring is this aldehyde and this ketone had to be bonded together in the alkene to be split apart in the ozonolysis. So the carbonyl, this one has a methyl on it, so there has to be a methyl off of the double bond. And then the other end of it had a hydrogen on it, so this hydrogen right there, that would work. Then from this carbon, which is this carbon number 1, if we number 2, 3, 4, the 4th carbon, 1, 2, 3, 4, the 4th carbon has to have a methyl off of it, but it has to have a double bond off of it also. So limonene has to have this structure where we have 2 double bonds in it. And a problem like this is really interesting because it makes you think about what the puzzle is. And yes, I know most of you are not going to be organic chemists, but it's the working the puzzle out that is the skill you need to get from this class, as much as being able to do organic chemistry. Okay, so the next review question, 3,3-dimethyl-2-butanol is reacted with HCl, HI, excuse me. A rearrangement takes place. What alkyl iodide would you expect from the reaction? So we need to draw a mechanism. So the first thing we're going to do is protonate our alcohol because we don't have a good leaving group. So we need to make it a good leaving group. Then good leaving groups leave, forming a cation. Then it's a secondary cation, so we need to rearrange it to a tertiary cation. And then the iodide can add to it, so we're going to get this 2,3-dimethyl 2-iodo-butane. 2-iodo 2,3-dimethyl-butane, okay, in the correct order. So the rearrangement is it goes from that secondary cation to the tertiary cation because tertiary cations are so much more stable.